Alright, hello. This will be an introduction to my video series on complex analysis. And basically, I have a couple video series on Calc 3 and set theory going on, which I will add to when I can. But basically, I wanted to do on complex analysis because it's a very exciting topic and it's more interesting to me than the other ones to do. And so that's kind of why I decided to start this one, even though I kind of have a few other playlists running. But basically, complex analysis, what is it exactly? Well, basically, if you remember from algebra, I guess 1 or 2, when you do the quadratic formula, sometimes you find out that the solutions to the quadratic equation, they can be imaginary. And, which is the square root of -1. I probably should have written it up here somewhere, that I is just equal to the square root of -1. Because it's not really a real number. There's no number that you can square, no real number that you can square, and you get -1. So that's why it's an imaginary number. Now, complex analysis kind of started like in the later 1800s, I believe, with some precursors to it a few centuries before. But I think it was Euler who really was really big into complex analysis, because he's the one who developed that formula, e to the I pi is equal to -1. And here I just have some very useful formulas that we're going to be going into later on. So, for example, this is de Moivre's theorem, and that's e to the I theta equals cosine theta plus I sine theta. I'm going to be proving that even if you haven't had complex analysis before, if you studied higher math, linear algebra, differential equations, you probably have seen this, at least have seen this, something like this. But I'm going to get more into it now that we're doing complex analysis, which will focus specifically on this kind of stuff. And of course, here I have the series expansion for e to the z, where z is a complex number. We're going to learn how to deal with complex sequences and series, which are similar to the real series and sequences, but there are some differences. It's not quite the same. And you'll see that a lot of times in complex analysis, a lot of stuff with real numbers works very well for complex numbers, like derivatives, very, very similar. There are like a few extra twists and exceptions that I will get into more when I come to that part in the playlist. And also, if any of you guys have studied group theory, ring theory, and field theory, which kind of build off each other, you'll know that the complex numbers form a field, and we're not going to get really into that so much in this playlist because it's kind of a different branch of math altogether. But basically, if you studied those, you'll know the complex numbers form a field because it's commutative with both respect to the addition and the multiplication operation. So it forms a ring, a non-zero commutative ring, and therefore it's a field. But again, we're not going to get too much into that. And and so basically, this is just a kind of like a basic overview of what I'm going to be talking about complex analysis. I'll start with the basic stuff like algebra and how to add and subtract, multiply and divide complex numbers. And then I'll get into more like polar coordinate representation. And after that, it kind of like really picks up like the very fancy formulas that go on in complex analysis. So it's very important to get the basics down first before I get to anything more complicated. So that pretty much covers all the introduction for this video, so I'll see you guys in the next one.